Professor Dunne has been stretching people's assumptions about reality for more than 40 years, going back to her groundbreaking work as manager of PAIR, the Princeton Engineering Anomalies Research Laboratory. Her focus on remote viewing, the human-machine anomalies have changed the accepted scientific paradigm within an inch of its life. She described for me having been too naive back in the 1970s to realize how controversial her work was. And I knew we were destined to be friends when she told me the following joke. Two parapsychologists are sitting in a bar. One says to the other, "Wouldn't it be something if the light at the end of the tunnel turned out to be New Jersey?" Since 1986, Brenda has served as on the executive committee of the International Consciousness Research Laboratories. Her son, Jeffrey, is here. He is chairman of that organization. Along with her late research colleague, Robert John, she is the co-author of the book Margins of Reality, The Role of Consciousness in the Physical World. Please join me in welcoming to the podium Brenda Dunne.
Well, hello again. And thank you for coming back and listening to me rant some more. I am delighted that Professor Resnick's left a door open at the end of his talk, and I think I might have something to offer that we can push through it. But before I get into the science of the subjective, is this okay? Can you? I'd like to read a brief excerpt from a paper that Bob, John, and I wrote back in 1997 by the same title, Science of the Subjective, because I think it lays a groundwork for what comes after. This subsection is entitled Scientific Currency. To consider its business effectively, any science must ordain a set of conceptual currencies in terms of which it can represent and evaluate its phenomenology. In most of the classical physical sciences, these currencies strive to embody precisely measurable and unambiguously quantifiable and strictly replicable properties, with minimal statistical variance. In the quantum-based physical sciences, however, as well as in the biological, medical, psychological, and social sciences, progressively more reliance has come to be placed upon statistical rather than uniquely deterministic measurables. In most cases, a cumulative sequence of three genres of such conceptual currencies can be traced, relating to tangible substance, energy in various forms, and information. For example, most early science tended to focus on the behavior of palpable matter, its gross mechanics, its chemical and physical properties, and such, with primary reliance on the quantitative measurable that we now call mass. Well, midway through the 19th century, the concept of energy, mechanical, thermal, electromagnetic, atomic, was added to the arsenal of scientific endeavor as a somewhat less tangible but still quantifiable currency of phenomenological representation. Over the past few decades, and this paper was written 20 years ago, a third scientific currency, loosely termed information, has taken center stage and clearly will dominate basic research and its applications in the foreseeable future. A similar conceptual genealogy has characterized the evolution of the biological and medical sciences. Early preoccupation with the properties of biological substance, blood, tissue, bone, cell, has led inevitably to the confrontation of the energetic processes of living organisms, their metabolism, their kinesthesiology, logical dynamics, immune and restorative activities. And at present, the overriding emphasis is on biological information, as manifested in the mechanisms of neurophysiological reaction and communication, immune response, brain function, genetic coding, and a host of psychophysical correlates. Originally, these three currencies of matter, energy, and information were presumed to be orthogonal, but subsequently they have been shown to be fundamentally interchangeable with immense consequences. Einstein's transmutation relation, E equals mc squared, that everybody learns in kindergarten, has impelled most of 20th century physics, and along with its technological, political, and sociological implications, which can hardly be overrated. Somewhat subtler equivalents of energy and information has also been established in various thermodynamic and quantum mechanical contexts and in basic information science itself. And this may well drive much of 21st century science and its applications. Hey, thank you. I hate reading to people, but as I tried to come up with a way to sort of summarize that, I discovered that that really summarized it. This business of the fungibility, the interchangeability of mass and energy didn't bother people too much, but when you bring information into the mix, you run into a problem. Information is hard to regard as purely objective. Oh, sure, I could take this article, I could scan it, I could quantify it and digitize it, and you will all get the same letters and numbers and whatever, but will it mean the same thing to everybody? There's a subjective dimension of information that is critical. Information doesn't mean anything unless it means something. I mean, I could take a bunch of letters and throw them in the air, and that's information. Is it? Does it mean anything? Where does meaning come in? Is the meaning intrinsic to the information that's in those letters and numbers and equations? Or does the meaning come from someplace else? Does it come from some intangible aspect of our being that organizes our experience in some way and makes sense out of it? That sort of raises the question of this very ephemeral, very difficult concept of consciousness. How do you fit consciousness into this currency? And if these currencies are fungible, then if information is both objective and subjective, then mass and energy should probably have some component of both subjectivity and objectivity. And therefore, is there a question of meaning when we start talking about mass? Is there a sense of purpose when we start talking about energy? Are they independent of our consciousness as science has previously presumed? Okay. That's the whereas. Let's go to the therefore. Let's return to this wonderful topic of quantum mechanics. Everybody likes to invoke quantum mechanics. We have quantum leaps. I've always thought it was interesting how quantum leaps, which in principle are very tiny, have come to mean humongous shifts of whatever it is that's leaping. But quantum mechanics is one of these areas where most people will say, oh, quantum mechanics is much too complicated, very few people understand it, and you have to know a lot of advanced mathematics to understand it. I don't buy that. I had, as a teacher and as a colleague, somebody who could explain quantum mechanics clearly and simply, in the sense that I forget whether it was supposed to be Heisenberg or Einstein who had said, if you can't explain something to your barber, you probably don't understand it. Well, Bob John explained it to me in very simple terms. It started out with a conversation we had very early on in our relationship when he said, what do you think is going on in these anomalies? What do you think is happening? And I, in my standard rambling, went on for maybe 20 minutes explaining what I thought was going on, namely that you had these two entities that were interacting, and Bob, God bless him, listened to me. Up until that point, most people I knew didn't listen to me. They tended to regard me as a little bit off the wall with crazy ideas, but Bob listened, and he said, that's very interesting. He said, do you know about covalent bonds? And I said, no, what's a covalent bond? He said, well, let me explain to you. A covalent bond is something rather straightforward. It's very fundamental to physics and chemistry and science. But you basically have two atoms. Let's take a trivial example of hydrogen. Now, I have to step aside here and say it took me years to get used to the pejorative tone of, I'll give you a trivial example. I found that most physicists, when they're trying to explain something to you in terms and equations that you can't possibly understand, will point out that they're giving you a trivial example. And it's a very intimidating term. One day I asked a physicist, a friend of mine, and I said, can you explain the difference between trivial and non-trivial? He said, sure. He says, trivial means in principle it can be solved. Non-trivial means it's impossible. Oh, that's interesting. I said, but when you're talking about hydrogen and you say that this is a trivial example, what happens when you start talking about something like oxygen or something like uranium? Oh, no, that's non-trivial. Oh, are you telling me then that the only thing you really know is hydrogen? And everything else is sort of an extrapolation therefrom? Well, sort of, Bob said, because after hydrogen you run into the three-body problem and it gets very complicated. And I said, what I think I hear you saying is that you guys really don't know much. But you do know hydrogen. Well, it turns out that the covalent hydrogen bond is very interesting. You have two hydrogen atoms, okay? Hydrogen has one nucleon, it has one electron, okay? And the electron is running around the nucleus. And if this one is running this way and this one is running this way, whatever that means, and that's a little bit vague also. And if the two atoms get close enough together, they will attract each other, and because they want to have two electrons in their shell because it makes them happy, they will start sharing their electrons, okay? So what you have then is a hydrogen molecule, trivial hydrogen molecule, that has these two nuclei. You have two electrons that are sort of spinning, this way around the nuclei. And what you end up with is something very curious. Turns out that hydrogen molecule has a greater energy than the sum of the energies of the two hydrogen atoms. Now, if you take atom A and atom B and you put them together, you get molecule AB, which has more energy. Where does that come from? Well, the physicists will tell us that it comes from some inexplicable, anomalous thing that they call the exchange force, okay? I'm not making this up. I mean it. I'm really not. I may be simplifying it, but I'm not making it up. Now, it seems that that exchange force is somehow associated with the fact that when you no longer can identify which electron came in with which atom, you have sacrificed a bit of information. That information has now morphed into a little bit of energy, okay? Anomalous energy, but an energy nonetheless, and an energy that is accepted by mainstream science as a real thing. Well, this was a wonderful conversation. I turned to Bob and I said, that's fantastic. That's so beautifully elegant, and it's exactly what I was trying to say, that, you know, like when you have two people and I'm here and you're there and we have an experience separately and then we share an experience, the experience for the two of us together is going to be different than the experience for us as individuals. Yeah, he said, that's right. Well, this led to several years of ongoing conversations because I became positively fascinated by quantum mechanical principles. Bob taught a graduate level course at Princeton on quantum mechanics, and he encouraged me to sit in on the class. And I said, oh, you know, I'm not going to be able to follow that stuff. And he said, no, ignore the equations and all the math. Just deal with the concepts. So I did, and the concepts were fascinating. After a few weeks of the class, one of the other grad students said to me, aren't you a psychologist? And I said, yeah. He said, well, why are you taking this course on quantum mechanics? Quantum mechanics? I said, God, I thought this was the psychology of subatomic particles. Well, it turns out that one can approach quantum mechanics that way. And Bob and I spent, as I said, several years taking apart quantum mechanics piece by piece and looking at the subjective aspects of each element, of each concept, of each principle, and discovering that one could translate them back and forth from an objective description to a subjective one. In fact, all of the concepts of quantum mechanics can be metaphorically transposed into aspects of psychology. In fact, we wrote a book about this. It's called Quirks of the Quantum Mind. And in that book, we took a whole array of concepts, starting with things like mass and energy and information. And we looked at it from the subjective side. So, for example, one could maintain, from the point of view of mass, that what I'm presenting to you here is kind of heavy, but I'm trying to present it in a light-hearted fashion. Now, let's talk about charge. Well, I'm really very excited to be here today to have an opportunity to share this with you, and I hope it turns you on. Let's talk about distance. I realize that some of the things I'm proposing are pretty far out, but frankly, they're rather close to my heart. Okay, you get the general idea. It was fun, and we did this, as I say, across a whole battery of concepts, and it works well. Turns out that when you think about it, quantum mechanics is the best, when I think about it anyway, is the best psychological model we have of human consciousness than anything else that I ever picked up in psychology school. It's elegant, it's beautiful. Why? Because quantum mechanics doesn't describe the physical world per se. Quantum mechanics describes our subjective experience of the physical world and our attempts to explain them or to define them or to categorize them. We're not describing what's out there. We are describing our experiences. Think about that for a minute. That's heavy. It's far out. well, I could go on the quirks of the quantum mind for some time, and again, time being somewhat constrained, if, you know, there is such a thing as time. And well, we can go there too. That one's fun. When you're dealing in the world of non-local events, time and space become particularly intriguing. And I have to say that that particular aspect seems to annoy most mainstream physicists more than almost anything else we've ever. Basically a wave that appears like no, it's a particle that appears. Anyway, they ended up getting so frustrated that Schrödinger packed his bags and went back to Austria. And Niels Bohr, who was basically a very jolly, pleasant personality, got really upset, and he growled at Werner Heisenberg. This story is told in Heisenberg's book. I'm not making this up either. He growls at Heisenberg. He says, "I can't deal with this anymore. I'm going skiing." And he takes off, and he goes up to the mountains to ski. Heisenberg, meanwhile, is left there wandering the streets of Copenhagen, things running back and forth in his head. A few days later, Bohr comes back, and he says, with his classic characteristic grin, "I've got it. I've got the answer. It's complementarity. It isn't either or. It's both and. The world is not dualistic. It's complementary. It isn't a question of whether it's this or that, but it's both of them." Now, my version of this explanation I refer to as the grapefruit universe. Let's assume that you get a package of 10 grapefruits, you know, from Florida, of course. I guess you're the guys down here, you don't get them shipped, but up in the cold north, occasionally we are blessed with a box of lovely fresh grapefruit, particularly in the dead of winter. And you open it up and you say, "Oh God, these look good." And you slice one open, and you know, there you see the sort of characteristic star-shaped pattern, you know. And then you slice open another one, and there's another star-shaped pattern. You slice up another one, and you say, "Gee, this is a different kind of grapefruit. This one has sort of crescent-shaped pattern. That's interesting." Well, you keep cutting them up, and it turns out that 8 of them have the star shape and 2 of them have the crescent. You say, "Well, I think I've just discovered a subspecies of grapefruit." There's the star grapefruit and there's the crescent grapefruit, and it's clear that the star grapefruit are the dominant species, because you can expect to see a star grapefruit 80% of the time, and you would only see the crescent 20% of the time. And, you know, if you're really good at it, you could write a scientific paper and so forth. But, you know, that's not really the answer. The real answer is it all depends on how you cut it. There aren't 2 kinds of grapefruits. There's one grapefruit, and it depends on how you look at it, okay? This is the essence of complementarity. There aren't 2 different polarities or 2 different conflicting views. There's one, and how we look at it will determine how we experience it and what sense we make of it. That is, what meaning we attribute to it. And it isn't just waves and particles. It isn't just position and momentum. It goes well beyond the world of quantum mechanics or even the world of physics at all. One can talk about the complementarity between subjectivity and objectivity. One can talk about the complementarity between mind and body, between science and religion, between Bhakti and Vedanta. These are just different ways that we perceive the world, and how we perceive the world, the questions we address to the world, determine the reality that we experience. And so, in conclusion, I would just leave you with this idea of complementarity as consciousness to get into the system and ever so slightly change the odds. It's not going to turn it upside down, but it will shift the probabilities a little bit. And this is really what our pair research found. I'm very fond of the concept of uncertainty, And I strongly believed that most of modern science would be more productive and more creative if scientists could acknowledge uncertainty and say the magic words, I don't know. I don't know. And when you don't know, there's room for new knowledge to come in. There's room to learn. Anyway, I will leave you with that. Thank you very much for your attention. And